Many control systems use a combination of the three types of feedback already discussed: proportional plus integral plus derivative, or PID control. The foundation of the system is proportional control. Adding integral control provides a means to eliminate steady-state error, but may increase overshoot. Derivative control is good for getting sluggish systems moving faster and reduces the tendency to overshoot. The response of the PID system can be described by equation 11.6, which simply adds together the three components required: the proportional, the integral, and the derivative. Another form of this, obtained by factoring out Kp from each term, is 11.6a, where the components all have a very familiar feel about them. So basically, the output of the PID controller is proportional to the error signal, the sum of the past errors, and the rate of change of the error. The contribution of each control is influenced by the associated gain constant, Kp, Ki, or Kd. You will by now be at ease with calculus and will have recognized the opportunity to complicate a simple system with calculus. Alas, not all systems are simple, and the use of calculus is likely as you start to model and control more complex systems. For this course, we will stick to the very simple maths, as we are more about the concepts than the maths. The controller that implements the PID equation, 11.6a, can be either analog or digital, but virtually all new installations are digital. A straightforward version of an analog PID controller that uses 5 differential amplifiers is shown here. The first differential amplifier U1 subtracts the feedback from the set point to produce the error signal. Op amps U2, U3, and U4 are configured to be unit gain, integrator, and differentiator amplifiers respectively. They produce the values for the three terms within the brackets in the PID equation 611a. The final amplifier U5 sums the three terms and multiplies the sum by the Kp to produce the output. The capacitor C1 on the integrator accumulates the error in the form of charge. And the capacitor CD of the differentiator passes only the change in error. The constants Kp, Ki, and Kd are selected by adjusting R1, R2, and R3 respectively. The circuit shown here can exactly implement the PID equation, but practical considerations usually complicate the picture. For example, all real amplifiers have an upper and lower limit, at which point they become nonlinear. Large and rapidly changing error signals may cause either the integrator or the differentiator amplifier to saturate. Should that happen, its output will temporarily dominate the output signal and may cause the system to go unstable. One problem associated with the integrator is wind-up. This occurs when a system is subjected to a large disturbance and the proportional controller or actuator, in its attempt to correct the problem, saturates full on. Because the system can't provide as much output as is really needed, the error condition lasts longer than it theoretically should. But all this time the integrator is accumulating. Consequently, when the error is finally reduced, the large accumulated integral factor may cause the control variable to overshoot. A solution to this problem is to have the integral control section disconnected when the system is saturated. Another problem with integral control is that the true integrator will sum all the error times time area since the beginning of time. It has been demonstrated that a better system results if the integrator slowly forgets the effects of errors from the distant past. This can be done by allowing the charge to slowly leak off capacitor Ci through Rc. A problem that can occur with derivative control is as follows. In a real control system, the set point is usually stepped up or down in discrete steps. A step change has an infinitely positive slope, which will saturate the derivative function. A solution to this problem is to base the derivative control on the feedback signal alone, PV, instead of the error, because the control variable, be it temperature, position, or the like, can never actually change instantaneously, even if the set point does. The PID equation for this method system is the output of the PID is equal to Kp times the error plus Ki epsilon E delta T plus Kd, and then delta PV over delta T, where PV is the process variable. Feedback from the sensor. The traditional form is more familiar to engineers comfortable with calculus. A practical controller must account for various real-world problems such as those just discussed, but typically the nature and extent of design modifications required are not known until the actual system hardware is tested. Changing the characteristics of the analog controller may require component changes and/or rewiring. A distinct advantage of digital controllers, which we discuss next, is that its response is governed by software, which is relatively easy to change, even at the last minute. A PID digital controller is essentially a computer, most likely microprocessor based. The controller executes a program that performs the same series of operations over and over again. First, the computer inputs values of the set point, SP, and the process variable, PV. Then it uses these data to solve the system equation 11.6 or 11.7. Finally, it outputs the result to the actuator or the actuator drive circuit. One distinct advantage of the digital system is that control strategies and parameter constants can be changed or fine-tuned by simply modifying the software. This diagram shows a sample error versus time curve. The following is a description of how the PID control equation 11.6a could be implemented with a microprocessor-based controller. The first term inside the brackets of the PID equation is simply the error E. Next comes the integral term Ki epsilon E delta T. As has been discussed, this term represents the area under the error curve. The controller samples the error at regular intervals of time t. A reasonable approximation of the total area under the curve is the sum of the rectangles, where the area of each rectangle is the product of t times the area E. This can be expressed in the equation form as follows. Ki epsilon E delta T is equal to Ki E1 ET plus Ki E2T plus Ki E3T. This is the equation 11.8, where Ki is the integral gain, E1 is the error at time 1, E2 is the error at time 2, and so on. T is the time between samples. Equation 11.8 is called a difference equation, and it is very easy for a computer to evaluate. The program simply records the error value E at fixed time intervals of t and keeps a running total of the Ki Et values. At any time, the integral term Ki epsilon E delta T equals this total. This diagram shows the flowchart for this segment of the program. Get the current value of error E, multiply error by constants Ki and T to form Ki Et, add the result to sum up previous values. Epsilon new is equal to epsilon old plus Ki times E times T. The The third term of the PID equation is the derivative component. The derivative, or rate of change, is actually the slope of the error curve. As shown, the slope is a function of the two most recent error values and the sample time t. Slope is equal to delta E over delta t, is equal to E3 minus E2 divided by t. The derivative term in the PID equation, 11.6a, is formed by multiplying the slope of the constant kd times delta E over delta t is equal to kd E3 minus kd E2 over t, which is equation 11.9, where kd is the differential gain, E2 is the error time 2, and E3 is the error time 3, and so on. T is the time between samples. Equation 11.9 is another difference equation that is easily evaluated by the computer. The program would subtract the value of the older error term kde2 from the newer error term kde3, and then divide the difference by t. This program shows the flowchart for the segment of the program. Get the new error e multiplied by kd to form the new error term kde new. Subtract past error term from the new error term. KDE new is equal to this, or minus KDE old. Divide the difference by t. Having shown how the individual terms of the PID equation can be computed, we can now put them together and present a flowchart of the entire program. As you can see, the general format of the controller program is an endless loop. For each pass through the loop, called an iteration or scan, 4 basic operations are performed. Read in the setpoint SP and sensor data PV. Calculate the individual components of error, integral, and derivative, and then sum these. Multiply the sum by Kp to form the PID output. Send the PID output to the actuator. A stable system is one where the controlled variable will always settle out at or near the set point. An unstable system is one where, under some conditions, the control variable drifts away from the set point or breaks into oscillations that get larger and larger until the system saturates on each side. This diagram shows the response of stable and unstable systems. An unstable system is clearly not under control and may in fact be dangerous if large machines are involved. There are many examples of the oscillating kind of instability in everyday life. Imagine holding a large wooden tray in your hands and trying to keep a golf ball, which is rolling about on the tray, centered at a certain spot. If the ball is on the right, you would lower the left side of the tray, but that causes the ball to roll past the center. Now lower than the right side of the tray to bring it back, and the ball rolls past center to the right, and so on. The ball ends up oscillating back and forth across the tray. A primary reason control systems go into oscillation is because of phase lag caused by the dead time or backlash, the interval between when the correct signal is sent and when the system responds. Consider the case of driving at a moderate speed down a narrow winding road. You would be making continuous, small back and forth adjustments to the steering wheel in order to stay in the middle of the road. Now imagine yourself driving down the same road, but in a car with a lot of backlash in the steering wheel. In other words, there is half a turn of free play in the steering wheel before the car actually starts turning. If the car starts to drift towards the right, you turn the steering wheel towards the left. With all that free play, however, nothing happens initially, so you turn faster. Eventually, the slack is taken up, but by this time you are turning the steering wheel so fast that the car veers to the left, so you start frantically turning the wheel to the right, and so on. Closed-loop control systems employ negative feedback, which means that the controller is always pushing the system in the exact opposite direction of the error displacement. If the controller variable happens to be oscillating, then the controlled force should be lagging by 180 degrees, because 180 degrees is the opposite direction for a rotational system. If there is any dead time in the system, the controller's response will lag even more than 180 degrees. In other words, if in an oscillating system, lag time causes phase lag, but the amount of phase lag depends on the frequency. For example, consider the case of a control system that is cycling at a frequency of 1 cycle per minute. If there is a 1 second lag between the controller output and the system response, then the delay is not very significant, as is shown in Figure A. However, if the entire cycle time of the system is only 2 seconds, then a lag time of 1 second is very significant, because the delay adds another 180 degrees of phase lag, making a total lag of 360 degrees. As Figure B shows, 360 degrees of lag is the same as being in phase, which means the system has positive feedback. Positive feedback occurs when the controller output is in phase with the motion of the control variable, so that instead of applying a correcting force, the controller is simply helping the control variable go in any direction it wants. It's only a matter of time before some disturbance will cause the control variable to be pushed off center, and when it does, positive feedback will take over if the system gain is at least 1 and push the controlled object to the edge of its range. Therefore, to guarantee that a system will be stable, the gain must be less than 1 for any oscillating frequency where the lag causes an additional 180 degrees of phase shift. A Bode plot is a graph that can determine if a system is stable or not. As shown, the Bode plot is actually 2 curves sharing the same horizontal axis, which is frequency in radians per second. The top graph shows how the open loop gain varies with frequency, and the lower graph shows how the phase lag varies with frequency. The system is typically unstable when the gain exceeds 1, when the lag exceeds 180 degrees. The curves shown here are fairly typical in shape. We can see that the system is represented by the Bode plot is stable because when the phase lag is 180 degrees, the gain is less than 1, 0.3 to be exact. 2 terms quantify the stability of the system: the gain margin and the phase margin. The gain margin is the gain safety margin, the difference between the actual gain and unity, taken at the frequency that causes 180 degrees of phase shift. For the system shown, the gain margin is 0.7, which is 1 less 0.3, which is equal to 0.7. The phase margin is the phase safety margin taken at the frequency that causes a gain of 1. For the system shown, the phase margin is 70 degrees. 180 degrees less 110 degrees equaling 70 degrees. The method of arriving at numerical values for the constants Kp, Ki, and Kd depends on the application. Traditionally, PID control was applied to process control systems. However, with the advent of small, fast, off-the-shelf PID modules, PID control is being applied to position control systems, such as robots, as well. In either case, a practical step-by-step procedure can be used to arrive at the PID constants. First, the constants Kp, Ki, and Kd are set to initial values, and the controller is connected to the system. The system could consist of the actual hardware or a computer simulation of the same. The system is operated and the response is observed. Based on the response, adjustments are made to Kp, Ki, and Kd, and the system is operated again. This iterative process is adjusting each constant in an orderly manner until the desired system response is achieved is called tuning. Certain modifications may be necessary to the basic PID equation to make the system stable under all conditions. Although many methods of tuning PID controllers exist, two of the most common were developed by Zeiler and Nichols and are called the continuous cycle method and the reaction curve method. The continuous cycle method, or closed loop method, can be used when harm isn't done if the system goes into oscillation. This method will yield a system with a quick response, which means a step function input will cause a slight overshoot that settles out very quickly, as is shown in Figure B. The tuning procedure is as follows. First, set Kp to 1, Ki to 0, and Kd to 0, and connect the controller to the system. Step 2, using manual control, adjust the system until it is operating in the middle of its range. Then increase the proportional gain, K'P, while forcing small disturbances to the set point or the process until the system oscillates with a constant amplitude, as is shown in Figure A. Record the K'P and Tc for this condition. Thirdly, based on the values of K'P and Tc from step 2, calculate the initial settings of Kp, Ki, and Kd as follows. Make Kp about 60% of K'P, Ki is 2 over Tc, and Kd is Tc over 8. Step 4, using the settings from step 3, operate the system, note the response, and make adjustments as called for. Increasing Kp will produce a stiffer and quicker response. Increasing Ki will reduce the time it takes to settle out to zero error, and increasing Kd will decrease overshoot. Of course, Kp, Ki, and Kd do not act independently, so changing one constant will have an effect across the board on the system response. Tuning the system is an iterative process of making smaller and smaller adjustments until the desired response is achieved. See Figure B. Example 11.6. A control system is to be tuned using the continuous cycle method. Initial settings were Kp is equal to 1, Ki equal to 0, and Kd also set to 0. By experiment, it was found that the system first went into constant amplitude oscillations when Kp was equal to 4. Figure 11.30 shows the system response during the experiment. Determine a first cut set of values for Kp, Ki, and Kd. From the response graph, we see that the period of oscillation is about 0.7 seconds. Therefore, Tc is equal to 0.7 seconds, and we can calculate the parameters Kp and Ki and Kd using equations 11.10, 11.11, and 11.12 respectively, where Kp is equal to 60% of K'P, which is equal to 2.4. Ki is 2 over Tc, which is 2.9 per second, and Kd is Tc over 8, which is 0.09 seconds. The reaction curve method, the open loop method, is another way of determining initial settings of the PID parameters. This method does not require driving the system into oscillation. Instead, the feedback loop is opened and the controller is manually directed to output a small step function to the actuator. The system response, as reported by the sensor, is used to calculate Kp, Ki, and Kd. Note that the actuator, the process itself, and the sensor are operational in this test, so their individual characteristics are accounted for. Because the loop is open, this procedure will work only for systems that are inherently stable. One test possibility is shown in Figure A. Here, the loop was opened by placing the controller in the manual mode. Then a small step function was manually introduced. This signal caused the controlled variable to move slightly, and the resulting position response was recorded. A typical response curve is shown in Figure B. Note that the vertical axis corresponds to the range of the process variable in percentage. The system constants are calculated based on the response curve as outlined on the next slide. So first draw a line tangent to the rising part of the response curve. This line defines the lag time L and the rise time T. Lag time is the time delay between the controller output and the control variable's response. Step 2, calculate the slope of the curve. N is equal to delta PV over T, where N is the slope of the system response curve. Delta P is the change in the process variable as reported by the sensor in percentage, and T is the rise time from the response curve. Third, calculate the PID constants. Kp is equal to 1.2 times delta CV over NL, where delta CV is the percent step change in the control variable. N is the slope as determined by equation 11,13. And L is the lag time. And finally, Ki is equal to 1 over 2L, and Kd is equal to 0.5 times L. Let's now look at an example. The reaction curve method is used to tune a PID control system. The system was turned on and allowed to reach a steady state middle position. Then the controller was placed in the manual mode and directed to output a small step function signal. The system response from the sensor was recorded. Figure 11,32 shows the step signal from the controller CV and the resulting response PV. From figure 11,32a, we see that the signal from the controller CV was a step of 10%, 40% minus 30%. Figure 11,32b shows that the system response PV. The PV went from 35 to 42% for a change of 7%. After constructing the tangent line on figure 11,32b, we read from the graph the values of L and T. L is equal to 0.2 seconds and T 0.9 seconds. Next, we calculate the slope of the response from equation 1113. N is equal to delta PV over T, or 7% divided by 0.9 seconds to give 7.8% per second. Now we can calculate the PID constants by applying equations 11, 14 through to 16 respectively. We get the values of Kp of 7.7, Ki of 2.5, and Kd of 0.1. These values would be used as initial settings, and the final settings would come from fine-tuning as discussed earlier. In a digital control system, sample rate is the number of times per second a controller reads in sensor data and produces new output values. Generally speaking, the slower the sample rate, the less responsive the system is going to be, because the controller would be always working with old data that were current when the last samples were taken. Another problem with the slow sample rate is that the controller may simply not be able to keep up with what's going on. Shannon's sampling theorem states that the sampling rate must be at least twice the highest frequency being monitored, or else aliasing can occur, when the collection of sample data is not sufficient to recreate the original signal. Figure 11.33 shown here shows this condition where the sample rate was slightly less than twice the frequency. Notice that the sample values would suggest a frequency 1/3 of what the actual frequency was. Of course, in a control system, the control variable is not usually tracing out a sine wave, it's more likely to be some random nonlinear motion. How would Shannon's sampling theorem be applied in such a case? To answer this question, we must invoke Fourier's theorem. Any function, sinusoidal or not, can be expressed as the sum of sine waves. It turns out that the more non-sinusoidal a signal becomes, say approaching a square wave, the more significant higher frequencies it contains. This means that to accurately follow a random path, a control system would have to sample at least twice as fast as the highest component frequency. In practice, a sampling rate of at least 10 times the highest visually apparent frequency in the system is usually sufficient. In most systems, sampling is done once at the beginning of each pass through the program loop. That is, one sample for each iteration. Therefore, the sampling rate is determined by how long it takes for the loop to be executed. Also, certain hardware functions take time, like an analog to digital conversion, typically 100 microseconds or less for 8 bits. Figure A illustrates the sampling cycle. Figure B shows one approach to speed up the sampling rate. In this case, the analog to digital conversion occurs at the same time as processing occurs. Although this increases the sample rate, Ts, it does not reduce the throughput time, Tp, the time for any individual sample to pass through the system. Let's look at an example. A microprocessor-based control system runs at a clock speed of 1 MHz. The system uses an 8-bit analog to digital controller with a 100 microsecond conversion time. The program loop that processes the analog to digital input requires 55 instructions with an average execution time of 4 clocks per instruction. If analog to digital conversion is not overlapped with processing, what is the maximum sample rate? What is the highest frequency that this system can monitor? So, the solution, analog to digital conversion time is 100 microseconds. The processing time is 55 instructions times 4 clocks, times 1 microsecond per clock, divided by the instructions is equal to 220 microseconds. So the sample time is 100 plus 220 microseconds, giving us 320 microseconds. The maximum sample rate is 1 over 320 microseconds, or 3,125 kilohertz. With a sample rate of 3,125 kilohertz, the system should be able to track a control variable with a periodic motion of that divided by 10, or 312 hertz. Auto-tuning is the capability of some digital controllers to monitor their own output and make minor changes in the gain constants Kp, Ki, and Kd. For example, a temperature control system might decrease its proportional gain slightly if the overshoot is beyond a certain threshold, and increase the gain if the response is too slow. Like manual tuning, auto-tuning is an iterative process, but because it's ongoing, the system can adapt to changes in the process. For this reason, controllers that use auto-tuning are known as adaptive controllers.